Okay, so the recording now has started.
Thanks.
Okay, so we'll just move on. Paul, are you doing the introduction to this, and I'll switch over when we get on to the slow step.
Yeah, absolutely. So what we're going to do is we're going to open up the Little Man computer, and you might have to scroll quite a way back up in the chat to find the links for that. Otherwise, just type a search in LMC Higginson. You know, that's probably quicker actually.
I'll find it and load it up.
And then I'm just going to talk a little bit about where students probably should have come from if you're picking them up at the end of GCSE and the start of Key Stage 5. And if you're in an institution that doesn't teach at Key Stage 4, maybe you're a sixth form college, or maybe you're a member of staff who doesn't have anything to do with Key Stage 3 and 4, you only teach Key Stage 5, then, you know, it might be useful to see where we think students should be at when they start the course. So Lynne, if you can just move us on a slide, or probably two. Yeah, here we go. So we're probably going to need to have just a minute or two to look at this, just to remind ourselves. Yeah, AQA. The AQA specification is very, very similar, and just to keep the volume of slides down, I just put the snip of the OCR version in. But there is hardly any difference between what students are expected to have experienced and know amongst the different exam boards. I'm pretty sure I checked the Welsh board as well. It was a while back since these slides were constructed. I thought that was the current version of the specification. It's not the A-level list, this is the GCSE. So just looking at a few details from that. Yeah, there's a question in the chat about people being muted. I'm getting a small amount of static. It's not too bad though. Lynne, you're on mute, by the way.
Yeah, I just said I was going to have a look.
Okay, so just looking at some of the details of this, in the bottom right-hand corner of that screen, we've got the von Neumann architecture, and it's got memory address register. So the memory address register, that register where the address we're trying to access in main memory is stored, exists in the Little Man computer. It's there and you can see it. The memory data register is a buffer for whatever's been fetched out of memory, and that doesn't exist in the Little Man computer. So we need to be aware of these things, and you know, it would be nicer if it all married up perfectly, but you know, sadly it doesn't. And you know, these are things we have to be aware of, and students will come across memory data register and it'll be called that. It won't be called memory buffer register, as you may see in some texts or searches that you do. So you know, we've just got to make sure that we're constantly using the correct terminology. Program counter exists there and the accumulator exists there. The thing that does exist in the Little Man computer is the current instruction register. Again, a similar idea to the memory data register. It's just a buffer where the current instruction can be held, perhaps whilst other stuff is going on with the data bus. There might be other things being fetched to allow an instruction to be completed. So that current instruction needs somewhere to live whilst all that's being busy on the bus. So the current instruction register is there. And, you know, I think it's worth going through the purpose of these registers repetitively, so that students get continual chances to practice. Okay, so that's what we've got at GCSE. This is where we should expect students to come from. And on the next question, we've got an example. On the next slide, we've got an example of the sorts of things they might be expected to know about. So I'll just give people a moment to read through that. I think the thing is that because at GCSE students don't have to read and interpret or perhaps write for themselves in assembly language, it can get skimmed over. But I think that the key point about using the simulator, the little computer, well, just picking up on a comment there that most of my A-level students haven't done GCSE. I guess it depends which exam board you're doing, but I would certainly bring them in at a low level and try and cover some typical GCSE activities. If you're doing OCR, it's not so bad, because it's the same process and the same instruction set as GCSE, so it's not too bad. I think, yeah, if you're doing AQA, you might want to use the LMC as an introductory stepping stone. You'd have to have a decision on that based on the knowledge of your own students. But the point is that even though we're not asked to write or interpret assembly language at GCSE, a lot of people do find it useful, because one of the big bonuses of studying an assembly language is it gives students a real handle on the architecture that they will be asked about. It gives them something practical to do. Now, I think we only had one person who said they were absolutely green on things, and I've got a link which I can put into the chat if you just want to step out and have a look at these problems whilst we go through some things that are a bit, perhaps a bit slower for the amber and red folk. Apologies if I can't remember who it was who said they were green. But when the Little Man Computer first kicked off as an activity back in the days of the pilot course of the GCSE, this was one of the few resources out there, and it was actually quite good. It's got some worked examples. It's got some things that you can repackage as problems for your students, and it really takes you through the whole range of the instruction set. So if you're nice and confident with Little Man Computer, and you'd just like to step away from the meeting for 10 minutes, maybe 15 tops, there's a little resource there for you to explore, perhaps have a go at coding up some solutions before you look at the answers. And I think Lynne is going to, and I will monitor the chat while that's going on, but I think Lynne's going to go through some introductory step-by-step basics of the LMC.
Yeah, so as Paul said, Paul, I'm getting a bit of feedback. Can you mute maybe?
I'll mute myself.
There, is that better? Yeah, I think that's better. So when we've done this previously, and when we've worked with teachers in other settings, we do find that quite a few people just haven't come across this before. So we wanted to offer this as a slow step point, whereby if you haven't come across Little Man Computer before, you've got this opportunity to go through it. And like Paul's explained, the second link on, or the second paragraph down on this slide, is if you have got that experience. So what we need for this slow step is the, can someone just put in the chat, are you able to click on the links on this slide from the screen? Because if not, I'll have to copy them across into the chat window.
I can copy them across, Lynne, I'll do that now, but I've put my headset on to try and reduce that feedback.
Yeah, that's better.
So that's gone in the chat now.
That's great, thanks, Paul. So the first of these is just a link to the Little Man Computer Simulator that you may already have open. And the second is a link to a document that Paul and I have produced, which is just going to go through a couple of examples just on a really slow step style. So I'm going to try and stop sharing these slides, and I'm going to share my screen instead. So let me get this back and I'll share screen instead. Okay, so hopefully you can see a split screen with the left hand. Oh, I've got the wrong window open, but in a second, I'll get across here. So we've got a split screen with the Little Man Computer on the left hand side and the PDF of the document which you should have on the right hand side. So hopefully everyone's been able to get a copy of that from the Google Drive. So what we're just going to do here is just step through. So this is the first site that you've got of this simulator. The left hand side here is where we're going to get some code. And then the right hand side is where we've got all our different memory addresses. So to start with, if we go to this select button at the right hand, at the bottom of the blue bar, and we're going to select the add. So this is a sample program that's already been written for us and introduced. So this is going to it's going to ask the user to input two numbers, and it's going to add those two numbers together. So you can see that the code here has been loaded into this top left-hand window. What we see on the right-hand part of this window is a similar representation of it, but done with just the line numbers down the side. And we'll come back to that in a short while. Then what we're going to do is from the options, which is just under on this green bar at the bottom of the screen in the middle, we're going to set this to be the slowest mode to start with, just so we can see what's happening. So we're going to choose default slow. Then when it's too slow, it will be too slow. But when it's too slow, we can choose to speed it up a little bit. But it's better to set it at that to start with. Otherwise, it just races on and you can't see what's going on. OK, so things to keep an eye on. We've got an output up here, which we'll get when we've added our two numbers together. And you'll see that there's a 02 next to it. That's the register number. Down at the bottom, we've got input, and that's got a 01 next to it, which we'll come back to in a moment. Then in this orange block in the middle, we've got the CPU, or representation of the CPU. We've got a 2-digit program counter. We've got space for an instruction register. We've got an address register, and then the accumulator. Off the bottom of that, we've got the arithmetic unit. So we need to keep an eye on those different fields. We've also got 100 different memory locations, memory addresses, 0 to 99. What we've got in the first 5 of these, 0 to 4, is a representation of this code. I don't know if you'll see, if I highlight that, you should see that. Yeah. What you'll see is the input has been translated as 901. To explain that, we need to look at the help page for the Little Man Computer, which I've got here. So if you scroll down, you'll see that there's a set of codes that are used for the different instructions, and we can see that 9 is used for an output, so or an input. So if we go back to our Little Man Computer, you can see that the first line of our instruction is to input a number. So this is asking the user to input a number. That's been translated as 901. We've just looked up what input was on the LMC, and it's represented as a 9. So the 01 is because input down here has got a 01 as the register. So 901 means input a number into register 01, which is this down here. Okay. So when we get to output, you'll see that instruction 04 is 902 if we look over on this top line of the memory RAM addresses. And so that means it's an input or an output, and it's going to register 2, which is this pinky purple one up at the top. Okay, so that's where we start. So then if we just scroll on to the next page, you'll see what I've done here is a step through of the execution. So we're going to just slow step this. There's a button called step. We've set it to go slow. So I'm just going to press this and we'll see what happens to start with. Okay, so we started off on the program counter. It's splitting, part of it's going to the arithmetic unit to add 1 to it, and part of it is coming off to the right. This blue one is going to go back to the program counter, so that's incremented ready for the next number. This is where it goes slow, so there's these arrows where I can just quickly click on it, increase the speed, slow it down again. So it's gone to address 0, it's picked up the 901, and you'll see it split that 901. So the 9 has gone into the instruction register and the 01's gone into the address register. So the 9 was an input and the 01 was address register 01. Okay, so it's now come up with, as you can see at the bottom, it's now come up with an input required instruction from this little, like an Android man there. So I'm going to just put in a number, let's say input number 5, and you'll see, I'll speed it up a little bit, 5's gone into the accumulator, and we're now on to, so it tells you here the input value has been loaded into the accumulator, and we've now moved on to instruction 1. So on the PDF on the right, you'll see we've had the increment PC step, we've had the fetch step where it fetched the 901 into the program counter, into the instruction register and address register. And then we've input the number and it's gone into the accumulator, which is the execute part of the cycle. So we have this cycle which happens each time we execute an instruction. So our next instruction, we're going to step through this and I'll speed it up a little bit. We've got the program counter that splits again. It's going to increase to 2 and get put back in the program counter for next time. We're going to fetch instruction 1. And you can be thinking what you think instruction register and address register might be this time. Okay. So what's happened here? Instruction 3. Well, we can see here we've got instruction 1, 01 is 399. So the instruction that's labelled 3 is a store instruction. So it's storing, and then this data here is actually a memory location. So it's stored this value 05 in memory location 99 down at the end. So 399 is to store whatever's in the accumulator in the address 99. Okay. We're going to do the same again. I'll speed it up a little bit. Again, program counter increase. This time we'll get the next instruction. 901, you've seen that before, so it's going to ask us to input another number this time. Okay, we've got the input required, so I'll type in 7 this time, press enter. That's going to go into the accumulator. So a quick question for the chat. Why did I need to store 5 in memory location 99 or any memory location? Why could I not just add 2 numbers straight together? Yeah. So you need another memory location to store 2 numbers, that because you can only store 1 number in the accumulator. Yes, addition. So Karen, yeah, addition is always done to what's in the accumulator. That's completely correct. Okay. So we've input our second number. We're now going to do this instruction 03, which is 199. So I'll set that running. So this is going to add the value in the accumulator to the value in 99. Speed it up a lot. So you can see the little man's gone, add the accumulator to contents of the RAM. That went quite quickly. If you noticed, it pulled the 7 plus the 5 into the arithmetic unit and put 12 back in the accumulator. Okay, our next instruction is going to output. We can see that that's set up as a 901. 9 we know is an input or output instruction for LMC, and 02 we know is this output register at the top. So I'm going to step through that. So it fetches the instruction, picks it up, splits it into instruction register and address register, and it's put the output onto that output register there. Okay, so that's worked through on the PDF that you've got. There's another example that I'm not going to go through, but it has the maximum of 2 numbers there. There's the code, it's part of the programs that are provided for you. So it's used one of those examples, and as before, there's this slow step. So if you've got students that want to go through this, you can give them this document if this helps, and it slow steps everything that the code is doing. Okay, so that's what I wanted to do for LMC. Are there any questions on that before we just move on? Well, move back to our slides.
The next activity is going to be similar. So if you wanted to let that sink in for the people who aren't really familiar with this, then that's going to be okay.
Okay. So in the absence of any questions coming through right now, I can always pop back to it, but I'll stop screen sharing my split screen and I'll go back to the slides, because like Paul said, there is an example coming up where you can do this, test something out for yourselves.
So I've just put some text in the chat, which should be copyable, unlike the text on the slides. And the idea is to grab that text and put it into the simulator, the LMC simulator. So you can either I must admit it's a habit of mine just to press the refresh button to clear it, but I think you can. I think there's a clear or a reset button on the simulator.
Okay, so that's the right code, isn't it?
Yeah. So what's in the chat is what's on the screen, so you don't have to type anything. And the idea is just to hang fire for a couple of minutes. And in the past, when we've run this, we've found that there's a significant number of people are not really that familiar. So this was a useful exercise, and I hope that is the case today. So the idea is to run it, play around with the speeds. And if you've got any questions about what that code is doing or what individual parts of it mean, to put them in the chat. And, you know, as usual, it's a case of no question, no question's a bad question. And David, I noticed you joined the call. Thank you. And I hope you can catch up with where we're at. We're running the little man computer, which is easiest to get by doing a search for LMC and then Higginson. Right, there's
the indentations LMC sorts out, I think, doesn't it? So even if you do put things in, it can correct.
Yeah, if it's putting extra line breaks in, it's probably just as quick to just delete them manually. I mean, there's only, you know, 8 to 9 lines of code there. Certainly quicker than typing it. And if there's any confusion about what individual lines of code are doing or what the general purpose of it is, then please put that in the chat.
So just to say, when you, or on my version, when you paste in a copy and paste Paul's code, you're absolutely right, it does give loads of new lines, but when you press submit, it seems to sort that all out and it gets rid of them all and indents everything.
That's okay, David. As I say, we're working with a sort of a pre-A level thing at the moment. We're concentrating on where students may come from at GCSE level, and we're working with Peter Higginson's LMC, the Little Man Computer, and Lynne's been through an example with us, nice and steady, and we've now got this second example which we're just investigating ourselves for a few minutes, and we're inviting any issues to be put in the chat.
Just to stress as well, so there's a few mnemonics on this example, on Paul's example, that we didn't cover on the slow step through. So for example, the break, the BRZ and the BRA, the other branch. If you're not familiar with these, if you click on the help button on the LMC page, it opens up that extra page that I showed you where you can scroll down and see what these instructions actually are.
So again, apologies to the people who are super familiar with this, but we will just have 1 or 2 more minutes to allow people to explore that example program. And if there's any of the functionality of the Little Man Computer that's causing a problem, or if there's any of the how the code works is causing confusion, please do put it in the chat. And for those doing OCR at A level, this is a program that may be the sort of thing that could appear on the exam papers, which at GCSE it wouldn't. They wouldn't be asked to interpret or add to code. Yep, in the chat that is correct. It just keeps accepting input and adds that input to a running total as soon as you type 0. The loop exits and that running total is output. And I think earlier on in the chat somebody made the comment about iteration and using these branches. So branch if 0 in this case it is how assembly language deals with iteration, and for that matter for selection. I think because you've run this, hopefully you can keep it on your screens, and there's a few teaching points that I'd like to go through. So apologies if you were halfway through that and you still want to explore it. Maybe that's something you can take away, but I'll just take that question out the chat. Yeah, I'll just go through it. So loop top is a label, and that's going to, when this is when the assembler creates effectively the machine code, that's just going to be turned into a reference number, which is going to dictate what the program count is reset to. So loop top in the human side of the language is just a label, and that's going to translate to changing the program counter in the machine version. So it's going to input a number, and if that number is a 0, branch of 0, you're going to go to another label, which for our convenience we've called exit. In the real computer, that would just overwrite the program counter and send it to whichever number that would be. Let's just count them: 0, 1, 2, 3, 4, 5. It set the program counter to 5. The instruction at position 5 is to load the total, then it will output it and halt stop. if the input, back to the top now, line 0 and line 1, if the input is not 0, that branch will not occur and will add that input to the total. The total is then stored, STA, I'm going to store that. And again, total doesn't exist in the memory. Total will be translated into a memory location. In this case, if I just count the line numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, it'll be memory location 8. So store whatever's in your accumulator into memory location 8. And then the BRA is branch always. So whatever is in the accumulator just doesn't matter whatsoever. We're just going to change the program counter to the index of loop top, which is 0. So the program counter will change to 0, and the next fetch will be from that memory location 0, and it'll be a 901. How did I know it was memory location 8? Because when the program compiles, is assembled, it just puts the instructions that you've typed into the next memory location in sequence. So loop top imp will go into memory location 0. BRZ exit memory location 1. So that's why I was counting out loud to work out that it would be in memory location 8. So I had to physically count 0, 1 up to 8 to find out where total was.
And can I just say, Paul, if people have it open in the simulator, that's the difference between the left-hand column of code and the second column of code. So the second column of code has done that counting that Paul was working out in his head. So you could also look on that second column of code and see that it's been translated as 08 space dat space 00. So there's a cheat as well if you've got the simulator open.
Just as an aside, when this first came out, and in subsequent years actually, one of the things you have to do in school is go from machine code to assembly language to higher level language. And I used to start with machine code, and students hadn't seen this LMC before. They'd not seen it before, and I didn't share the instructions with them, so the mnemonics were not known to them. And I used to provide them with like a crib sheet of the machine code, but not using the mnemonics. I do it in a verbose way, and they would write their programs, and to decide where something was kept, in this case total dat 000 means we're going to have a variable, we're calling it total, it's going to hold data, not instructions, and its initial value is going to be 0, and the computer will just decide for itself that that's going in memory location 8. And I used to get them to pick a spot, like pick something you can remember, maybe 66 or 99, and it doesn't matter where the memory location is, as long as there is one. And I think that helps getting students over the idea of what a variable is. That it's a named location that contains a value that you can overwrite at any time you like. Anyway, just to stay on that idea of teaching points, I think this little man computer, whether you have to use it or not, which at GCSE you clearly don't, although at OCR level you would, what's the benefits in the classroom? And I think what Lynne did when you're talking through that fetch, decode, execute cycle, it brings that to life far more than reading it in the book. And in that assembly code window on the left of the screen, you've also got the option in the options menu to look at opcodes and operands, which isn't at GCSE, but it clearly is at A level, and it just splits up the code into what's the opcode, that's 0 through to 9 opcodes, and which part of 901 or 312 or 808 is the operand. And you can use the little man computer to talk about opcodes and operands. I also like the Little Man computer for the way it allows students to visualize RAM. You know, we talk about RAM all the time, even from Key Stage 3, but what a fantastic representation of it. I know it's very limited in that there's only 100 memory locations, but it really brings it home to me that RAM, yeah, the single digit in the opcode is 9. Yeah, Lynne referred to them as registers 1 and 2, and I guess they are. I always refer to it as 9 means we're going to do some input or output. If it's a 901, it's on channel 1. If it's a 902, it's on channel 2. And that was my language for that. So yeah, I think the visualization of RAM is great, and it shows the connection between RAM and the processor. No, you've not missed anything. It's great. It was just me talking. We're just going through the teaching points that using the Little Man computer can throw up. I think it's also brilliant for the idea of a bus. And I used to have some pictures that I used to show to students of big fat chunks of copper, which were the original electrical engineering buses, and they could be tapped into. And it's a little bit like that in a computer. It's this big connector that the different memory locations can access and different parts of the processor can access. So what is a bus to most students? Is it something you get on at the end of school? And because you can see the buses in Little Man computer, I think it gives them a better handle for what a bus is. And when it comes up in the exam, it's not quite so strange. I think the other thing that's great, and looking at the slide on there, it's really hard to read the details, but you can see, right, I'll pick that chat question up in a moment, but you can see the blue outline, the assembly language code window. In the right hand portion of that, you've got things like in the second line, it's line 01, STA 11.
Oh, sorry.
And that means we're going to store something, whatever's in the accumulator, we're going to store it in memory location 11. And when we've got those labels in the left hand side of the assembly language code window, it's got first and second, for example, for the data, they completely disappear when the code is assembled. All that they are when the code is assembled is memory locations. And I think that's good for students to understand the relationship between those words they're using in the higher level language and the idea of a memory location. I'm just going to pick up, how does this code stop when you input 0? Well, that code on the screen isn't the code that we work with.
I'll go back to that one.
Yeah. You can barely read that code on the slide I was talking to. That was just an overview to remind me of things. But yeah, if you input a 0, the next instruction is branch of 0. And the branch is to branch to line 5, which is to load the total and then output it. I hope that's okay.
So can I just say, it may be obvious, but equally it's probably doesn't harm to say so. If the first word of each instruction line is one of those 3-letter mnemonics that's recognised by LMC, then that's obviously what the instruction is. If it isn't recognised, it's assumed to be a label. And that's what disappears when you convert it into assembly, which is what Paul was just talking about with the line that's exit and the line that's loop top at the start.
And those comments in the chat are absolutely correct. The other thing that I think is worth noting is that LMC uses decimal numbers, and I think we do have to go back to that stage where we say in the memory there isn't a little box that says 311 in it. That's just a bit pattern which is represented by the different states of the transistors in there. And that is correct. Exit is a label. Yeah. So if you notice on line 1, counting from 0, 0, 1, BRZ exit, exit is completely lost, as Lynne said. Exit just disappears when it's compiled, and it's just a memory location. And it will, well, actually, it's the branch instruction causes the program counter to jump to a value that matches wherever exit was placed in the code. The National Museum of Computing has been mentioned in the chat. I believe that's Doon South somewhere. Is that the one at Bletchley Park?
Yeah.
Yeah, it was. It's a long way from Cumbria to Bletchley Park, so we
We've
never
got
made
similar
that.
ones in Manchester, though, in one of the buildings at Manchester University. They've got some of the old machines there, which I think do the northern equivalent.
They've got one of the original machines in Manchester at the Museum of Science and Technology, is it? I can't remember what the museum's called.
Yeah.
But
and the university building, I forgot the name of it. It's famous Manchester academic, Oxford Road, Manchester.
yeah, I missed the boat on that, I'm sorry to say. So decimal numbers, we've got to be aware of that and get students to just perhaps highlight it with them. I've already mentioned the fact that some people, myself included, have used the Little Man computer and programmed directly into RAM. And I think that goes back to some of the historical things that Lynne was talking about, which is that's how you programmed the computer. You actually configured the machine to run a program. There was no stored programs that you could just load up. You configured the hardware to run a particular program. And I think that's more or less what you're doing when you're typing directly into RAM. And if you didn't ever try that before, try it. Try and write yourself a little simple program that perhaps just takes 2 inputs, adds them together, and outputs the answer by not using any mnemonics. Just type into the RAM locations. So I think there's there's an absolute wealth of things you can do with Little Man Computer. There's a few things coming in the chat, so I'll just have a short break to read those. Right, we're on our day out. Right. What we're going to have a look at next is, I guess, something that you might come across if you were doing OCR at A level, but perhaps less so at AQA. And it's just a little exercise which we can combine. Do you think, Lynne, we can combine this with having a quick comfort break?
Mm-hmm.
It's just a little exercise for you that you might want to give to your students to try and get them to interpret some assembly language. Now, in AQA, they're going to have to do this, but they're going to have to do it with a bigger instruction set. At OCR, they're going to have to do this with the LMC instruction set. So I think it's a worthwhile exercise for us to have a go at, and one that you probably would want to pass on to your students. So we're going to have a little break, and during the break, we're going to try and write in a higher level language of ourselves a version of an assembly language program that's going to be on the screen. So Lynne, if you should just oh, by the way, yeah, that link's there if any of you want to go back and look at that link, which if people stepped out during the step-by-step presentation, it'll be there in the slides when you get them emailed.
So I hope I've just done the right link and pasted it in the chat if the slides aren't clickable. And that's the code that you want, isn't it?
Yep. And I'm not... Do you want that in the chat, or do you want to actually type it yourselves?
Isn't that the same as you had earlier?
Yeah, I think so. But in fact, we don't need it in the chat. We don't need it in the chat because we're not going to do anything with it in LMC. We're going to write in a higher level language of our choice. So if you want to write something in Python that does this, if you want to write something in Java or in VB.NET or whatever it is, have a go. And if you've never tried to translate one of these programs into a higher level language program, I think it's maybe a good exercise for your students. So maybe we should try it first. And if you want to put your solutions in the chat in a few minutes, that's fine. And please do go and get some water, go and get a coffee and a biscuit. Take a little break. And should we set a time on this, Lynne? Should we say 20 past?
Yeah, I was just looking. So it's 12 minutes past now. So if we draw back together at 20 past, that gives you time to do this high level language and, you know, comfort break, drinks break, whatever you want, get some fresh air.
I think most people on the call can probably write the code for this in 2 or 3 minutes in their language of their choice.
So maybe just a forward pointer as well about after the break, we'll be moving on to issues that we find at A level.
Lynne, I'm just going to stretch my legs for 1 or 2 minutes and then I'll be back to monitor the chat. Is that okay?
Absolutely, that's fine. Yeah.
Right, thanks.
So just to pick up on Karen's comment in the chat, as well as this example that we've got on screen at the moment, this is where you can use any of the examples that are actually on the simulator as well. So there's the add example, just looking now, max and so on. I've got the wrong page open at the moment. Select add or subtract, max. When you get onto some of the others, they get quite complicated, like you've got a bubble sort in there and a about overwriting memory locations. So just stick to the first three, but they're very good examples to do this exercise with, of translating into a higher level language.
Lynne, do you need to step away for a few minutes at all? Or are you okay?
I probably shouldn't I? Otherwise I'll need to in half an hour.
It's up to you. It's 18 minutes past anyway. Excuse me 1 minute, people. I'll just be away myself. The doorbell's going. I think that Python solution is really good to have on my screen right next to the LMC version. You know, it really makes it hit home how readable higher level languages are. Okay, so there's a couple of people are actually typing in the chat, so it's 20 past 3, but we'll just hang fire till those comments have been typed. So we seem to be finished. So I hope that's something that you find that you can use in your classrooms with your students, and you know, there's all sorts of rabbit holes you can go down with that. It's hopefully a fertile thing to do. Lynne, could you just move us on, please? So this is just a reminder of what we've been doing so far, the rationale for putting assembly language in the curriculum, and what sort of uses we can make of LMC. And for those of us who don't teach GCSE, you know, maybe what's the most we can expect. And next we need to move on to A-level issues. And we've got two fairly different situations at AQA and OCR, but I think it's worth looking at both of them. You know, it widens our experience, and who's to say that we're not going to move schools in the future, or we'll have it imposed on us that we're going to have to change exam board. So, you know, not too much in the way of apologies for dealing with them separately. And first up, AQA. And I've put a box around what's different from the LMC work. That we have branches the same as we do, like branch always being unconditional and branch to if a condition is met. But we've also got these compare instructions in AQA. And we can compare two values. And if they're the same, then we can do a particular branch. Or if they're different, we can do a particular branch. We've also got the bitwise operators. So where we're performing these operators on bit patterns, you know, maybe on 8-bit versions of numbers, which I guess is in both specifications, but the simulator does it too. And we've got the logical shifts, and shifting left and shifting right, I think, are in both specifications. It's just that the AQA simulator deals with them. The OCR people, if you've got to deal with these things, you might still want to jump on with the AQA simulator if you think it's going to be useful for your students. And if we just have a look at the next slide, which is on OCR, and I'm afraid that I can't answer that question in the chat. Do you know if Educast has an instruction set? I can't tell you off the top of my head. So this is just to emphasize that the LMC instruction set, which we were looking at for the first section of the session, is right there on the A-level specification for OCR. The difference is that at GCSE, you might be expected to recognize the difference between machine code, assembly code, and higher level language, but you wouldn't be expected to actually interpret an assembly language program, and you certainly wouldn't be expected to edit it, add to it, or do anything else with it. But at A level, you will. The AQA simulator can be flipped between decimal, binary, and hex modes. And that's another reason that I've mentioned there, that people who are teaching OCR A level might want to jump onto the AQA simulator, even if it's only briefly, just to perhaps demonstrate some features of those, you know, the different number systems. But first up, we're going to have a look at the OCR work, which is
just to say as well. So Paul's talking about the AQA simulator. We will see that in a few moments, and I will do the same. I'll share the screen, split screen, and we'll go through an example really slowly just to show some of the differences as well on that AQA simulator.
So it's a pretty slow step, you know, it's a pretty small step to go from traditional GCSE use of the little man computer to A level. And before I start putting things in the chat, before I start copying and pasting things in the chat, I'd like people just to have a look at this past exam question, whether you do this board or not. So have a look at the question and just see if you can work out in your head what each line of that's doing. And we're going to need 2 or 3 minutes for that. So we're not going to follow up with the actual question just to respond to the chat. We're just using this as an example to go through it in our heads to see what we think it would do. So at GCSE, we'd be wanting to do some really simple programs just to really focus on the architecture. At A level, students are expected to be able to understand what's going on. So in this case, that an input is requested, and I don't think we need to run this. You can do that perhaps after the session's over. But an input is taken. One thing I can't work out in this simulator is 0 positive. Yes, 0 is a positive number. Yep. I can't remember why 0 is a positive number, but it is. The mathematicians amongst us will let us know in the chat shortly, I would imagine. But this one takes an input, stores it in a place called entry, loads up another value, which in this case is 5, and takes the entry away from that. So if you're typed in a 3, it'd do 5 minus 3. If that's a positive number, it jumps to a place in the program called accept and loads what it calls green light, which is just a 1, and prints it out. If you don't get a positive integer, including a 0, when you've done the subtraction, it does the loading of the red light. So the branch of positive does not fire. It loads the red light, which is a 0, and then it jumps with an unconditional branch to the end, print and end, and it outputs the 0 that it's loaded up. So it just outputs a 1 or a 0, depending on whether or not the input was 5 or below. And I don't think that's a big step from some of the very simple examples that we would typically use at GCSE. So if we can just move on, Lynne, the actual question didn't just say explain what this does. It wanted to know what was happening with the hardware, as that program was running. What were the various buses and registers doing during? I can't remember if it was 1 or 2 of those operations. And it's perhaps unnecessarily complicated by the way that the OCR theory section of the specification refers to more features than are actually present in the LMC, which is a shame, but at least the LMC gives us some practical that we can hang those on. One of the things there that is indicated in the second bullet point is the idea that the control bus dictates whether we're reading from a memory location or writing to it, and we just don't really see that in the Little Man computer. We don't have a control bus that goes into some sort of color-coded read mode or write mode. We just don't have that. So not anything we can do anything about, but worth recognizing. In the next slide, we've got a question where we've got the program, but we've got the actual question that students were being asked for. And you might be quite surprised to see that if you've not come across this question before, that it's a 6 marker. 6 marks, that's going some, isn't it? Explain what is happening when LDA1 is being executed. Not even fetched and decoded. We've got LDA1, we know what to do with it. What happens during the execution? 6 marks, that's a lot. So I'll just hang back and let people have a little think about that. You might want to scribble it down. If you were a student, what would you write if you were in that exam? Maybe write it down on a piece of paper, but there's no need to put your answer in the chat. And just picking up on the comment about 2's complement. I think in the 1's complement system there are 2 versions of 0, which is one of the reasons why 2's complement is more useful. There's only one value to check against to see if it's a 0. So we only need to look at that initial digit. Well, we only have to look at the whole set. We don't have to look at 2 different options for the first digit. The Renault mustn't have been using 2's complement. Interesting things, French cars. In the tour, you know, at the beginning, I said one of my things, Lynne does things with sheep, and I do things with bicycles. One of the things they have in the Tour de France is hill climbs, which are category 1, category 2, category 3, category 4, and then there's one called hors category. You know, it's like above categorization. And the original reason for that was that back in the day, like in the interwar years or whenever it was, they had this French car that used to drive up the hills. If it would get up in 4th gear, it was a category 4. If it could get up in 3rd gear, it was category 3, and so on. And if the car couldn't get up the hill, it was or category. It was above categorization. But that's nothing to do with assembly language, is it? So, having thought about how the heck would you get 6 marks out of this, what the exam board were after is that students are aware there was some sort of buffer to put the address, the memory address register, where are we trying to address in memory, and that the address bus picked up the value from that. The address bus then became live with that memory address, and in parallel with it, the control bus was saying we're going to do a read value, and that the contents of that memory location were therefore read, and that meant that their contents were transferred to the data bus. So the data bus becomes live with that bit pattern, and the memory buffer register then reads from the data bus, and that value is stored there. When it's in storage there, the accumulator can access it, and that value can be copied over to the accumulator. So you've got, you know, a good 6 stages there, 6 pieces of architecture that are being mentioned. I'm not 100% sure. It's not that old because it came from the OCR website, and I don't think they do kind of historic or no longer relevant questions. I haven't got a reference on the thing as to exactly which year it was, so apologies for that. We are going to have a quick look at another OCR question though, so if Lynne can just pop us onto that. And we don't need to try and... I know I got it just by going onto the OCR website and, you know, past questions. It won't be secure because I've lost my login. I finished teaching a year ago, and I lost my login then. So it's, and I didn't teach OCR at A level. I only taught AQA, so it's definitely in the public domain. So I would suspect it's from the current spec. So this is another question which we're just going to need a minute or two to look through. And I think, you know, just to keep things fairly brief, we don't need to try and interpret every single line of this program. What we're looking for is in the sentence, we want one instruction that when the program's executed, it changes the value in the program counter. And if you were watching Lynne's demonstration earlier, you know, that is absolutely crystal clear to students if they're familiar with stepping through LMC programs, that when you get to a branch, the effect of the branch is just to reset the program counter to some previous or future instruction. So it then becomes unnecessary to look through the whole code. We can just pick one at random, you know, go halfway down the program, it says BRA fail. Right, when it hits that, I'm not going to, let's see, line 3, it's going to go back to line 3 of the program. So in the LMC, the program counter would be reset to 3 whenever you hit BRA fail. So any of those branch instructions, if they are executed, are going to change the program counter. I'm pretty sure all of them. BRA test, yeah, for sure. Branch always goes to test. And test is about line 7 or 6, whatever it is. Some of them, like branch if 0, won't change the program counter unless the condition is met. And I haven't got the mark scheme to hand, but I would always go for the branch always ones because there's no ambiguity then. So we've got BRA main, BRA fail, BRA test. They will definitely change the value in the program counter. That's how branches work. And in the examiner's report, you know, it did indicate that that wasn't particularly well understood. If we've done the practical, you know, I'm sure it would be. So those are some questions that we've got to refer back to when we get the slide deck, and maybe, you know, consider the sort of teaching strategies using the LMC that we can use to overcome any difficulties with them. But I think it's time to move on to the A-level instruction set, and there's a bunch of links there which I'll just paste into the chat. Sorry about the formatting, but those are the 3 links. And we'll just give people a moment to get all their tabs sorted out. I don't think we're going to be referring to the Little Man computer again in this session. So if your screen's getting a bit cluttered and you want to get rid of some tabs or windows, you could maybe put the LMC stuff to one side. Or if you've got Lynne's slow step, you might want to save a local copy of that. Okay, so hopefully people can use the chat to get up to speed with getting those links open and accessible on their screens. And if Lynne, if we could just have a quick move on and talk about input and output, because in the LMC we've got this opcode 9, which works on channel 1, the input, and channel 2, the output. If you're doing AQAA level, there is no input or output. It simply doesn't exist. I like the input and output when I've been dealing with GCSE in the past. I think it's really useful. Students want to be able to input numbers, get answers, and see the output. But in Little Man Computer, they're not there. sorry, in the AQA exams, they're not there. It's solely about moving values from one register to another, or in and out of memory. And for the purposes of, you know, being practical, we're going to stick with that system. The ARM-like simulator, just from the chat, the ARM-like simulator is a development of the original AQA simulator. And if you look at the questions on the AQA past papers, I don't think there's a massive need to get into that ARM-like simulator. I think it was something that didn't sit well with its creator, Peter Higginson, and some other commentators. It didn't sit well with them, that it wasn't quite as realistic as it could have been, the original AQA simulator. So we're going to initially look at the standard AQA simulator. The link is about 3 or 4 comments up in the chat, and there are 3 bullet pointed links. The top one is the instruction set. The second one is the actual application, and the third one is Peter Higginson's own kind of commentary and help on it. So we do need the AQA simulator. And as we mentioned earlier, thanks, Lynne. As we mentioned earlier, in reality, the whole thing works on electrical states or levels of resistance in electrical components, transistors. But in the AQA exams, we're going to see decimal versions of everything. Now, we do need to know about hex and binary for any specification, but for 90% of the time, we're going to keep to decimal when we're dealing with assembly language, because that's what we'll see. Lynne, could you just move us on a couple? And again, so this slide is in there to remind us that what we see in the AQA simulator is what we've got in the specification. So on the left hand side of the screen is a question from an AQA paper, and if you've got the AQA simulator open, all the things that are on there are in the simulator. It's a lot more tightly matched than the situation was, if you remember, when we were dealing with the OCR theory section of the spec and the LMC. So hopefully that, you know, this hasn't got those issues that you've got to highlight with students, that that there's differences between what might be in the exam and what's on the simulator. With the AQA simulator, it should be all the same. And I think it also applies to the OCR. The things that are on the simulator are the things that they will need to know. Taking in from the chat, I think you're absolutely right. Memory data register is what the GCSE version of the OCR spec uses instead of memory buffer register. Excuse me. Whether that's the case at A level, I've not got that at my fingertips, but it's a good point. Thank you for making it. Just a quick look at the next slide, Lynne. Just some sort of issues that have been thrown up. Right, so we've got that MDR, MBR conflict at A level as well. Thanks. So I think that these issues are really helped if you've done a lot of practical, either with LMC or with the AQA simulator. Like, you can, when you use the AQA simulator, you can see the registers. They're there on the screen. You can see that all they do is hold bits of data temporarily. And any confusion. I mean, the examiner's report mentioned confusion about the purpose of a register, in that they've got no decoding function, they've got no transfer of information function, they're literally just holders. And I think students that have done plenty of practice with the simulator would naturally see that and wouldn't have an issue with it. Likewise, as I alluded to earlier, the buses are clear or more clear to students if you look at them in the simulator repeatedly. So they just mirror a bit pattern in a register or in a memory location. And, you know, I guess we'll need to roll hands dirty with this simulator. And I think Lynne's going to walk us through.
Yeah, so we're going to do the same as we did last time, and try and I'll stop the, I'll just move on one, I think. Yeah, I'm going to try and do the browser and the PDF together, so hopefully you can see them on your own browsers, in case they're not clear enough on the screen. But I'll stop sharing my presentation here, and I'll try and do the same as I did last time. Okay, so at the moment I've still got LMC up. I can get rid of that. And this is the AQA simulator. So it looks different. And also if you scroll down, I forgot what page it's on, page 5 by the looks of it, there's an AQA simulator example in those notes that I gave you earlier. So the same document that we had earlier. Oh, which PDF? Do we have the link for it? I'll probably find it again. Share, get link, copy link. Oh, Pete, well done. I think you got there first. So is that link okay for Jamie? Great. Okay, so just exactly the same sort of slow step as we did before. Just, you may not be familiar with this. You may have students who aren't familiar with this. As Paul and I have said already, I think it helps to get familiar with the LMC, the Little Man Computer, first, rather than going into this. But assuming that they've had some experience, there are substantial differences between this and the previous simulator that we've done. So if I just reset everything, as I was obviously working on something before. So right, we're going to click on the add program again. So the same as we did before, just you can try the other examples, you can write your own and you can load those in at some later stage. But for this first introduction to it, again, this is the same example we had before. It's going to ask for input of 2 numbers from the user, and it's going to add them together and output the results. Again, we've got the option to do a slow step. The default is faster. Again, if you've got students looking through this, it's worth doing it on slow, and then the students or yourselves can speed it up as and when you run through it. Oh, thanks, Paul. Hopefully that extra link is the correct one now. So at the moment, I'm still just working on the AQA simulator. So what I've also going to do is I'm going to, here you've got an option to do decimal, which is what Paul was just talking about, binary, which is just hard for anyone to interpret. The registers on the right hand side, just they're just too long to make sense of. And you've also got the option for hex. So you can choose which view you want from this. So I've just suggested it will be hex, and that allows us to just compare values as they go in and out of the registers from to and from memory. It could be using decimal, but I've just chosen to do this using hex just because they seem to be easier to compare. And then what to keep an eye on here. So as in the previous one, we've got input and output fields down at the bottom, marked in this blue, these blue empty boxes. We've also got our arithmetic and logic unit again here. I don't know if, can you see my cursor or not? I don't think you can you? Or maybe you can just. So yeah, arithmetic logic unit. This time our program register is slightly different. We've still got a program counter, but can you see it's at the top of this rectangle of registers? So we've got a program counter that's just in with these other 13 registers. So registers labelled from 0 up to 12. So there are different additional 13 registers for our use. In our examples, well, in this one, you can see we've got R0, R1 and R2 in use. So they're just going to be these bottom 3 registers. On top of that, we've got our current instruction register again. As part of our control unit, we've got our memory address register here, and our MBR memory buffer register, which as we've already put in the oh, I've got a question. Can you share your screen, Lynne? Is it not showing? Paul,
Lynne,
can you
I can see your
confirm?
screen. Yeah, I can see your split screen.
Yeah. So Dan.
What you can't see is you can't see the individual characters. You can see where things are on the screen, but you couldn't read individual characters particularly easily.
Okay, because that's because it's so small. If you are stepping along with this, if you have the simulator up in your own browser window, all I'm doing is I've loaded the add program, which is the sample one. So if you can see, there's this drop down menu at the bottom left hand side of the screen, and all I've done is selected the add one. So hopefully that's okay. So yeah, I was just talking about the different registers. You've got the MAR and the MBR, and the MBR is the one that we've just had that discussion in the chat about whether it's known as the memory buffer register or the memory data register, MBR or MDR. And then we've got on the top right hand side, we've got 4 memory locations, 0, it's not going to show me, 0 through to 1. So, sorry, 0 through to 4 as representations of our assembly language instructions. Okay, so I'm going to do exactly the same again as before. So we've got a slow step guide here, and we're going to go through this now. So I've set it to slow execution, and then I'll just speed it up. So the program counter has gone to the incrementer and increased ready for 1. And in parallel, you've got 0, it's gone and fetched the instruction from memory location 0 and put that in the current instruction register. So you can see that's actually come through the memory buffer register. So the memory buffer register stores the same data, which is the memory data from the memory address, as the current instruction register. And that data is the first instruction, which is a coded version. It's not quite as straightforward as it was with the LMC. The LMC at this point, we had 901, and you could do the lookup for that. You could see that the 9 was an input or an output, and the 01 was the register for input. So this time, we've not got that direct mapping from the EF010002. It's a bit more complex that, but what that does mean is it is this input R0, comma 2. So here, this time I should say that the input register is 2, or the input location is just labelled 2, and if it's an output, it's labelled 4. I'm not quite sure why they've adopted that, whereas the LMC used 1 and 2 there, but for the AQA simulator, it's got 2 and 4. So this time, again, it's asking for input. We'll do the same as we did last time. We'll input 5, hit return, and you can see that that data is now going to go, and it's been put in register 0. So this one, we had an accumulator before. This time we haven't got an accumulator, but it's put it into register R0. Okay, we can step again. and you can see it's going to increase the program counter and go and fetch the extra, the next instruction from the register. Okay, this again, if we look back to our code, this again is inputting a number from the user. So we're going to do the same there. Hit return. And this time we can see from the instruction that we're putting that into, so we're going to put that into register 1. It's trying to let me edit the code. So we've now got register 0 has got a 5 in it and register 1 has got a 7 in it. Now this immediately makes our code a little bit simpler than we had before. Don't you remember when we used the LMC, we had to put something in memory location 99 because all we had was the accumulator. That's the only place we had in working memory to store the information. So we needed to store it in RAM as well. So here we've got the 2 data values being stored. Our next instruction is an add instruction, and that's going to put the answer into R2. So we're going to step through that again. Program counter gets incremented. We're going to fetch the next instruction, goes into the current instruction register. It's executed by going to the arithmetic logic unit. And this time it's dropped a C, which is 12 in hex. So here we can show the effect of looking at it in decimal as well. Okay, so there we've got our decimal numbers in the registers. But what I was meaning is the MBR bus always shows the instruction in hex. That doesn't change. When you flick it onto decimal, it doesn't change those registers. They stay in hex, which is why I suggested to start with that you show the hex so that you can see that this instruction here has gone, well, which one are we on? We're on this one here. So the current instruction that we're on is instruction 2, and that's in that memory buffer. So I would, even though we work with decimal, I would recommend just keeping it in hex just for those first fetch parts of these cycles. But then, as I say, when you've done the addition, you can flick and show it in decimal if you so choose. Okay, we're virtually there. The next one is the halt. Okay, oh, sorry, I missed the output. So we output the number 12. We've got that in our output box down here. And then, sorry, the final one is the halt. It fetches the instruction, puts it in the control unit, and then everything's halted. Okay, are there any questions on that? So on the PDF, as well as the slow step that I've just worked through, I've repeated the AQA instruction set, and I've also given an example that I know students have liked working with. So Paul's already mentioned that we don't use the input and output, we don't see that at AQA and an OCR, but students do like input and output. So what there is just admit someone. So what there is there's a bit of code that I've made, and I'll just copy it across. And we'll share this as well. And what this does is it outputs the numbers, the letters A to E. Okay, so there's a worked example there about outputting a sequence of characters as specified by their start and end codes. So if you want something for to practice with the students on this, you can use this example, and there's a worked example that finishes the slow step document that you've got on PDF.
Lynne, there's a question in the chat. Can you explain the numbers below 0, 1, 2, 3, 4 when you are in decimal mode? So 0, 1, 2, 3, 4 being the columns of the main memory.
Let me catch up with you.
So
okay, so I've gone back to the
I've
gone back to the add example.
Yeah, on line 0 of the main memory, column 1 is 0, 0, 0, 0. The next column is 0, 0, 0, 1.
Oh, okay. Yeah,
Those
what we've
column
got,
references are
the column
just,
references here above here. So this is just going to be, if you take that 0 and add it to those. So you've got 0, 0, 0, 0, 0, and then you've got 0, 0, 0. It's an indexing mechanism. So this field here is 0. Oh, it's going to want me to edit it. Is 0, 0, 0, 1, and then the next. So numbers when you are in decimal mode.
so the numbers are just the instructions, which are a bit less transparent than the LMC. As Lynne said, 901 means we're going to do a 9, which is input or output. The 01 indicates it's an input. Whereas the code, the numerical versions of the code in this AQA simulator aren't quite as transparent.
Yeah, I did dig into that. We had a previous session where we were looking at this and the same question was asked. And there doesn't seem to be, I mean, there must be an explanation, but it doesn't seem to be clear at all. I've tried working it. If you look at hex, if you look at the instructions when the hex, I've tried working to see if the actual, the first part of it is consistent with input or output or the different registers, and I couldn't spot the pattern. So you've probably got students that will dig it out and work out what that is. But I didn't get there in the short amount of time I spent trying to find out what the mapping was. So LMC, really clear mapping between the instruction code and the mnemonic. In the AQA simulator, I haven't worked out. Yeah, homework set for next week. But I don't know if you'll get an answer. I haven't worked out what the exact mapping is. There's some things that look similar. There's some bits that you can understand. But as a general rule, I haven't worked out what that mapping is. I'm sorry.
The Halt as 0 comes up with all zeros, though. There's an easy one to
Yeah,
start with.
that one works. Yeah. But it's a good question and yeah, great homework. So I looked at it in binary, I looked at it in hex, I looked at it in decimal, and I still didn't really get any clues. I thought hex would be the easiest because that's what's used, as an alternative to binary. And I thought it might be in blocks of the 4 bits, but I couldn't work that out. Are there any other questions before we go back to the slides? Okay.
Okay, so my sort of angle of this is that I was just in the classroom until fairly recently trying to get kids through the A-level exam. And so what's coming next is something that might be useful to you in that sort of day-to-day ground. I've put the link again to the AQA document, which explains the instruction set for their A-level version. So that link's now just gone in the chat. We're going to need that. We're going to need to have that to hand. And the other thing we're going to need is a past paper question. And if your students have done some simulator work and you've done it fairly thoroughly, I think they'll find the assembly language questions in the exam papers really straightforward, and they will be what we call low-hanging fruit for them. So the link on the screen is not clickable, I don't believe, and in any case it's wrong because I've put scroll down to question 12 as part of the link. So that question paper is linked to in the chat. You'll need that, and you'll need the AQA instruction set, which is also there in the chat. So just giving people a moment to find those links and scroll down to question 12. So we're going to need to have a few minutes to read through question 12. And then we're going to sort of try and dissect it. So just to break in, the question that I hope we've got on our screens, question 12 in that paper, has got some pseudocode in there. And basically it's saying that if a character code is greater or equal than 65, so it's an A or further along, and it's less than or equal to 90, which is the Z, and they're capital letters, then it's going to increase the encrypted code by whatever the key value is. So if we're Caesar ciphering with a shift of 2 or 3 or whatever it is, we're just going to add 2 or 3 to that character code. If it's outside those bounds, we're just going to leave it as it is. The if statement won't fire, we'll go to the else. But if we have done the shift, then we're going to check that we haven't exceeded the Z value, and then we're going to deduct 26 from it to sort of go round the clock if we were using a traditional cipher wheel. So that pseudocode's fairly straightforward. The issue is, do we have good familiarity with the way that this would work in assembly language? And Lynne, if you could just bump onto the next slide. That's, you know, that tells a story, doesn't it? Less than 50% of the candidates were able to fill in the first part of the question. That, you know, this is a very, very easy question if you've had the practice. So the fact that less than 50% of the candidates were able to do that was poor, and likewise, only 10% got all the marks for the second part of the question. And you know, for me, I think these are easy questions. All we've got to do is give the students plenty of practice. So we start with ourselves, and what I'd like us to do is have a go. Now, we've got about 50 minutes left of this session, and I'd like us to hog 10 minutes of that to see if you can, you know, manually copy, or even, in fact, you can probably do it electronically, but copy the code that we've already got from figure 13 on question 12. It starts with compare what's in register 1 to 65. Get that code into the AQA simulator, get the crib sheet, if you like, the PDF that I linked to a couple of comments up in the chat. And if you're not massively familiar with it, that crib sheet will help you to understand what's been done already. And then you will be able to have a go at filling in the gaps 1 and 2. Now, particularly for those who aren't familiar, you're going to be flicking back to your tab with the AQA's instruction set on, and then flicking back to the AQA simulator constantly to try and make sense of that. If you are fairly familiar with it, you'll probably do this much quicker, in which case you get a little extra tea break. But time now is 16:10. What I'd like to do is monitor the chat for 10 minutes and give people that time till, well, 9 minutes now, till 16:20 to try and come up with a coded solution in the simulator. I'll put myself on mute so I'm not tempted to interrupt. to answer the question from the chat, yeah, if you want to test it out, you'll need to type something in, or you'll need to do a move, like just put a line of code in that moves some actual number. So precede the number with a hash. So just an example of how to put something in a register. I'll just put it in the chat. So in the chat, if you wanted the value 72 to be in register 1 before you start the code that was in the exam question, that's an example of what you'd put in. And that's a really good point. So thank you for making that. Obviously in the exam, they didn't need to actually write the program and run the thing. They just needed to figure out what's happening. If we want to test it with examples, clearly we need some values, and that line of code in the chat is how you do it. So it's 4:20 now, and yeah, so it might have been incredibly challenging if you weren't familiar. If you weren't familiar with the instruction set, but at least it might be a time to get started. The value 65 is in the register R1. I think the purpose of R1 is to hold the ASCII code for whichever character you're going to want to do the Caesar shift on. In the code that's provided, if I can just flick windows, in the code that's provided, the 65 being the limit of the capital A and the Z at the 90, they are preceded by hash characters in the code that's in the question. That means that you're dealing with the actual value, 65 or 90. They're not memory locations. So we're not using direct addressing. We're not directing the processor to go to some place in memory. We're using that immediate number. So if you wanted to, you could put a 65 in R1, but that just would signify a capital A. And I guess you should maybe try your code out if you're one of the people who've succeeded in getting something that you think's workable. Try it with something fairly high up the alphabet and give it a reasonable shift to make sure it doesn't go outside of the bounds of the capital alphabet. But as I said, it's turned 20 past. Some of us will have got a long way with that. Others will have been scratching their heads. So what I'd really like to do is to go through what the code on the question is on about and a possible solution. And normally there are more than one ways of answering these. Lynne, could you move us through?
Yeah, I was just picking up on Rachel's question. I'm not sure if we've answered that properly. So I might be misunderstanding it, but if we look at the first line of code, it's got to compare register 1 with this hash 65. So what's in register 1 is presumably what the user has as input for the character code that needs to be encrypted or not. So what we're doing there is we're checking if it's within this right range. So we're checking on this line, this first line, whether it's above 65, and then on the third line, whether it's below 90.
And in the chat, sort of 3 comments up, is how you would put that value into register 1 if you actually wanted to write the program and test it. And that in the exam question, it's not there. They're just assuming that the value has been put in register 1. And
yes, yeah. So that last one, yeah, R3 is the encrypted code. That's going to be your it's the
result of
the
the
value,
encryption.
yeah, plus the key value. That's correct.
Yes.
And yeah, because that's added R1 and R2. I think it's really sneaky on this exam question, because I think when you first see it, you would want to know what was in those registers, and it wouldn't have done any harm to have shown that somewhere.
Well, I'm going to do it when I go through the answers.
Yeah, students don't get the benefit of that in an exam, though.
No, they don't.
Okay, so I'm moving a slide on. I think you asked.
Yeah, we're going to go and we're going to talk through. Just skip that one. That's fine. If you want to come back to this later, the example solution is on that Google Drive. Yeah. Who was it who answered it? Karen. Register 3 is the encrypted code, R2 is the key value, and R1 is the input code, and it's going to hold the encrypted value if it gets shifted. If it didn't need shifting, it'll just stay as the original. So that was 12.1. And then we had to fill in these gaps 1 and 2. So here's my solution with a load of comments put on. And what we need to look for is down near the bottom, there is a label, do not encrypt. And I've written ##, which is yeah, sorry, in the chat, it just goes straight in. That's absolutely correct. So on the screen, down near the bottom of the code, we've got a label that says do not encrypt. Then the double hash is to indicate a comment, and I've written position 1 because in the question that was it was labeled with 1. So this is where we're at if you're switching windows and looking between the question and this example solution. Now, if we're not going to encrypt it, where it says move, so MOV, pretty easy to remember, that's move. Whatever these mnemonics are, the first register that's mentioned is generally where you're going to write something. And that, I think, takes away some of the confusion if you're new to this. So the first register mentioned is where something's going to get put, or an answer is going to be generated and put there. So move R1, move R3, R1, we're just going to take whatever was in R1, yeah, this business about input and output is a bit of a pain, because in the AQA exam there is not going to be any input or output. So I didn't use the input and output with the AQA simulator. I never used it, and I'm afraid I can't really answer questions about the channel numbers and how it distinguishes between that and registers. I think that they're just numbers. They're not preceded by an R, so they're not registers, and they're not preceded by a hash, so they're not immediate values. So where it says MOV R3 R1 below do not encrypt, the first register is where we're going to put something. Where we're going to get it from, R1, and R1 is where the value, the unencrypted value, is going to be. And we need to forget about input or output if our mission is to just get students through the exam. There is no input, there is no output. I wish they hadn't have put it in there. And certainly there isn't any text input or output. So let's get this clear in our heads if we're new to this, that the first register after any mnemonic is where the result's going to go. In the move case, we're moving from R1 to R3. It's as simple as that. And the reason we end up at do not encrypt is because effectively the if statement from the pseudocode told us that it was outside the bounds of 65 and 90 in the ASCII code. Therefore, we weren't going to encrypt it. We're only going to encrypt capital letters. So I hope that MOV R3 R1 makes a bit of sense. Question, well, it was part 3, but what's missing from position 2? You'll notice that I've put another comment higher up that says position 2. It's about halfway up the code, position 2. So that the code that's below that for the next 4 lines is the gap that students are expected to fill in. So at position 2, we have done the shift. In the preceding line, we've put a value in R3, which was the original value, the unencrypted code, R1, plus or added to the shift. So if we can just look at the previous line of code, add R3, R1, R2, it's the same format. The destination is the first register. So we're putting something in R3. It's an add, so we're adding R1 and R2, the original code plus the shift. So so in position 2, we've got R3 currently holds our shifted value. Now it might be that we picked something fairly low down the alphabet, like a Y or a Z or something, and we've tried to shift it and it's gone out of range. We need to check for that. The way that this compare works, CMP compare, is it just compares 2 values, and a compare will always be followed up by a branch. There are different forms of branches. In this case, we're looking at a less than. It could be a greater than, it could be a BEQ, which is equal to. But when it's not the same as the LMC. It's not just branch if positive, branch if 0, or branch always. When we do a comparison, we've got options as to which branch we do. So we're comparing the encrypted value with 91, and if it's less than 91, we're going straight to finished. At if the value isn't less than 91, so we've gone around the clock, if it were, we're going to do this subtraction. We're going to subtract 26, and the reason the hash is there before the 26 is because that indicates that it's a value of 26. It's not a memory location, it's not a register, it's immediate addressing. We're going to do the subtraction with a number 26. Same system as before. We're going to put the value, the destination for the result of this subtraction is going in R3. And the inputs are the original value of R3 minus 26. So we're doing that round the clock business. And then the branch has got no condition to it, it's just branch finished. As soon as you've done that subtraction, get yourself straight to finished. And at the finish, we stop. Effectively the output is R3. That's the shifted code, and we don't have to worry about input and output channels. And I'll just check the chat. Yeah, R2 is the shift. R1 is the original version of the original ASCII code. R2 is the amount we're going to shift it by, and R3 is the answer. So, for example, if we look at do not encrypt, why couldn't R3 be used to hold the shift? Because in the code that's already been written, it's evident that R1 is holding the original value and R3 is going to hold the encrypted one. For sure, we could have put them in R anywhere. You know, R7 could have been the encrypted value. R3 could have been the original value, you know, the plain text. But by looking at the top end of the question paper, you know, it's got CMP R1 #65. We're comparing R1 to 65. R1 is evidently the original sort of input, although I hesitate to use that word. When we do the encryption, we're storing the answer in R3. So I'm looking at line 5 of the code, just above position 2, add R3, R1, R2. When we've got an instruction like add, the destination is the first register. So the destination of this addition is the R3. R3 has got to be the encrypted version. The add line is on the question paper just above, well, on my screen, on the slides on the screen, it's just above halfway, just above position 2, where that # comment is. Sorry, / comment, position 2, the add line is just above there. You can see that R3 has got to be the register for the encrypted code.
Yeah, so the add line was part of the original question that we looked at from that A-level paper. So that's why it's add R3, R1, R2, because that's just taken from the question.
And then where I've done / position 2, that comment there, the double slash, is indicating that, yeah, the code I'm doing now is what was required on the paper. And it's absolutely right. You could choose any registers you like to have the original value, the plain text, the shift, and the encrypted version. But we can infer from the question that R1, R2, and R3 hold values we've been through.
So Pete's question there, we have to assume it. I think we have to deduce it. We have to deduce it from the code that we've already got. Now, it doesn't really help us because we have to work with what we've got on these sample questions. But if we were setting this at university, we would get pulled up because we would be expected to reduce the cognitive load and we'd be expected to say what these registers were intended to hold rather than having to deduce it. Because that's not actually what we're trying to test here. We're trying to test if they can understand the algorithm and its expression in assembly.
Clearly, we don't know what they are. We don't know what's in R1, but again, by reading the question, we understand that it's an ASCII code that may or may not fall within the capital A to Z range. Perhaps that's why only 10% of the candidates filled in R2 correctly. It is a bad question in that respect, but I do think that it's a good question if you want to get used to the instruction set. So if you were to ask students to write what I've put in that orangey shade next to the example solution, you know, can you make this into plain English? So the top comment, put 72 in a register. It says move R1, comma, #72. If you could give them the task of writing those comments in orange, it'll force them to go into the crib sheet, which by the way is provided in the exam, and it will force them to unpick what mov R1, comma, #72 means. And I do agree that it's a high bar. And I found this with my own students. You know, when we first came across this, it was, you know, it was double Dutch to some of them, and they really, really found it hard to get started. But once we sort of stepped into it and gave these explanations and gave them practices to do, they picked it up surprisingly quickly. I'm just going to read what's going on in the chat.
Yeah, Karen's just explaining the deduction that I talked about, you know, the fact that you can deduce that the register 1 is being used to compare with 65 and 90, which you know are your A and your Z. You know that the add instruction has got an R3 in that very first position. And by looking at the crib sheet, you know that that's where the output goes. So the only register that we've got left is the R2, and that must then therefore hold the shift.
Like I say, it's you know, on first sight, for somebody who's not used to all of this, it is a complex question. There's a hell of a lot to unpick, but I think that's what makes it a good resource for going through things with your classes. And some people might not be very happy about this, but I've got another one. But I think if you go through the process, if you go through the process for yourselves, I think you can perhaps have better success with your students. So the next question, Lynne. We seem to have disappeared from our presentation.
Yeah, my presentation just seems to have gone blank. I'll try and get it back up again.
Some people would be quite happy about that.
I don't know why that suddenly, I didn't click on it, it just went black. There we go, that's the one you want.
Yeah, I know it might seem tedious, but I can't quite articulate it, but I think there's value in actually typing some of this stuff. And what I think there's less value in is the next step from this AQA simulator, which was Peter Higginson and colleagues attempt to make it more realistic, where the address registers were all divisible by 4, for example, and there are certain differences with the immediate and the direct addressing. They tried to make the simulator more like a true ARM processor, and I think for your bread and butter A-level kids that simply doesn't matter. So I'm quite happy to not go too deeply into that side of the session and stick with the main AQA simulator. And I think it's got value to try and, especially if you're not massively familiar with this, is to actually hard code that, actually type that out. Now, what you'll have to do is manually type a value in memory location 100 and memory location 101 and 102. And as you work through this, you'll perhaps start to realize what it's doing. And the reason I've put this in is because the other question drew in a lot of the instruction set, but it didn't deal with the logical shifts, and this one does. That's why it's in here. It's also useful. It's got another compare and branch, which do take a bit of getting your head around. So that reminder about typing into the memory for 100, 101 and 102 is there. It's there to copy. And the values to put in those 3 addresses, 10, 50 and 80 are there on the screen. So again, I'll put myself on mute. I'll monitor the chat and we'll come back to this in about 10 minutes. Please do pop in the chat if you want to ask anything. So as you're working through it, if you don't understand what one of the lines is doing, just ask and I will interpret it.
So Paul, I'm just looking at the sample OCR paper that's online, that's publicly available, and that does have, it's the LMC, but it does have input-output, which surprised me based on what you said.
The OCR will do.
Just the AQA that doesn't do
It'll
the
be 901 and 902, or what are in and
just
out.
text. Yeah,
in and
it's
out.
just the AQA, is it?
The AQA strictly does not use input and output, but the AQA simulator has got that facility. And I just steered well clear of it. There's enough to worry about without adding anything else in. And also, if you get students used to using input and output, they don't get as familiar with this idea of just dumping something in a register, and that counts as an output. And in the exam questions, that's what's going to happen. So the encrypted value in the previous question was just dumped in R3, and it's the same in this question. R4 is going to take the answer. It's going to be a 0 on one condition or a 1 on the other. So
that's where we differ at uni as well, because we do use input output to illustrate, to show what's actually happening in the different well, you can do it in the simulator. You can output in decimal or hex or characters, or you can choose that number at the end. Depends on what the data type is for the output.
Yeah. So this one, R4, is going to get a 1, which is like a tick, or a 0, which is like a cross.
Thanks, Paul. I just spotted the input and the output on the OCR version.
Just to answer the question in the chat verbally, it'd be quicker than typing it. A logical shift left, if you can imagine binary digits in little compartments, like in little hotel rooms in a corridor, and you were to move each digit to the left 2 places and then fill in the empty gaps with zeros, that would be a logical shift left. So if you did a logical shift left by 1 place and your binary value was 1 1, you'd shift both those ones to the left and fill in the vacated gap with a 0, so become 1 1 0. So a binary 1 1 decimal 3, shift all those characters to the left one, and you've got a binary 4 and a binary 2 and then a 0, so you've got a 6. A logical shift left by 1 position doubles the number. So in our program, the LSL R2 follows the pattern. That's the destination. We're going to do a logical shift left on whatever's in R1 and stick the answer in R2. But instead of shifting it 1 place, the next parameter says #2. We're going to double shift it. So we're going to quadruple that number. So in the interests of not going past 5 o'clock, just to run through this program, LDR, we're going to load something into a register and the destination is R1. We're going to load it from memory location 100. There's no hash in front of that 100, so that's directing us to memory location 100, and we would have had to have manually typed a 10 in there. We're then going to logically shift that by 2 positions and stick the answer in R2. So the value suggested was a 10, so we're going to quadruple that, make 40. We're then going to put in the destination R1 the original value of R1, which was a 10, and that quadrupled number we just created. So there's going to be a 50 in R1. We're then loading up into this new register R3 whatever value is in 101, which is also a 50. So this thing is going to check that whatever we typed in when multiplied by 5 is whatever's in the next register, in the next memory location. And it does a compare, and again it's useful to check out the syntax of this. We're comparing that value of 50 with the quadrupled and add it to itself, also a 50 in R1. We're comparing those, and following a compare we get a branch. So we're going to branch if they're equal to label A. Label A tells us to put a 1 in R4. So if whatever was in memory location 100 and 101 are a number and then that number multiplied by 5, we're going to put a 1 in there, a tick. If we don't branch if they're equal, we're going to stick a 0 in there. Mov R4, comma #0 is the value 0. And then the B after that means we're going to branch. There's no condition, we're just branching. We're going to go to label B. And I'm not quite sure where the 80 comes into it.
No, I agree, Paul. The only time that the memory address 102 is used is when you're storing, and that's to store the value of R4. So the 80 can't get used anywhere, can it?
Yeah, I don't get that.
It's another example of to throw people off the scent, I reckon.
Yeah.
That's a
But
good idea.
R4 is going to get a 0 placed in it if we didn't do the branch if equal. Well, it's like a tick and a cross. It was one number and 5 times that number, or it wasn't, the 0 being it wasn't. But why we then subsequently go and put an 80 in there is beyond me. I have no answer for that. It could be, as it says in the chat. Lynne, there's one comment I'd like to make about the successor to this AQA simulator, which personally I don't believe is a necessary part of the A-level spec, but I think it's an interesting project that goes with the ArmLite simulator. Richard Pawson has written a really good book, and the best thing in that book, in my opinion, is a little countdown game. And this is what I use to get my students really familiar with this AQA instruction set. You don't have to use it with the ArmLite, you can use it with the original AQA simulator. And in fact, it's easier to show by an example. Could you just zoom along to slide 47, where it's got example from a book? Example from a book. So you give the students the numbers, and I've put an example there, 5, 15, 9, 24. You've got a target of 101. So you can use those operations from the AQA instruction set, and you can code whatever you like. So you put 5, 15, 9, 24 into some registers, and then by adding, subtracting, shifting, or using a logical OR operation, you can see if you can get in your target register the value of 101. And some of the students are really, really good at this. And the more they practice it, the more they get used to this AQA syntax. Now, they are given the crib sheet in the exam. It's in the paper, but the more they're familiar with it, the happier they'll be. And that, what a great idea that Richard had when he wrote that in his book. It's a fantastic teaching resource. It really is good for getting students to be familiar with things. So encourage you to go through the code, encourage you to get students to write the commentaries at the side, and I encourage you to play the countdown version with this to gain familiarity. Lynne, I think we're just a couple of minutes before 5 o'clock, so we're probably going to have to wrap up there. And the idea of this was that we would sort of get confidence with the AQA simulator if we hadn't really come across that before. And for those of you who've not really delved into it, I hope that this is a start. It's certainly not a packaged up solution, but it's a start to getting used to that simulator and the syntax. And obviously a reminder of some follow-ups. If you need to get in touch with us, our email addresses are on that website there. You'll be getting this slide deck. There's no need to write that down. And for sure, do consider getting your students to use the Isaac platform, not just for the assembly language side of it, but for all aspects of the A-level spec. You know, it's just it's a fantastic free resource. Why not use it? And Lynne, do you have any comments?
Yeah, it was just to follow up on the Isaac platform again. So there's a set of questions that they can attempt on there that includes, you know, it goes back to addressing modes, opcodes, opands. You can select whether or not you're following OCR or whether you're following AQA. It's got in preparation for the GCSE ones. It's got the other exam boards there as well. So yeah, I'm just flicking through what else have we got. Addressing modes in more detail, so it's got questions on that. So yeah, just have a look through the questions.
Lynne, there's
Isaac
a
as well.
question in the chat about how we get access to the recording.
It will download onto whatever it's called on my computer when I've finished. So yeah, we could put it up on our Cardinal Hume YouTube channel. That's probably the best place to put it. And again, when we post out the slides for today, we can send out a link to that. It might just delay things. Would you prefer to have the slides straight away? Because I don't know how long it takes to download, upload. We send out the slides straight away after the
Lynne,
session.
I think we should send the slides out pretty much straight away, and I'm not going to be able to stay here for much longer. I've got to leave, and then I'll be back later this evening. So in terms of uploading it to the YouTube channel, that could take a while.
Yeah. So what we'll do that, we'll mail the slides out straight away, and then whenever the cogs have turned and I've got a copy of it that I can upload, I will do that. We'll use our Cardinal Hume YouTube channel.